Hello, and welcome to Class 2 of Tidybiology. My name is Matt Hershey, and I'm glad that you're still with us. In Class 1, we went over the differences between R and RStudio, and we learned a little bit about the language and about how language has objects, and it has functions, and functions are essentially operations to these objects. We also learned a little bit about the RStudio integrated developer environment and our Markdown files, and how we can intersperse code and comments and notes to ourselves and analytical steps. So today we are going to dive into a package called dplyr. And dplyr is part of the tidyverse, and it has a group of functions that allow us to make transformations to data. This is one of the fundamental packages that we use for data cleaning, for data analytics. And so today is going to dive deep into different functions and how they work within the R environment. Let's dive in. All right, welcome back. I don't think we've lost too many students in the 2 days since the last class, so I appreciate your bravery. Today we will have a guest lecture by Akshay. But before we dive into that, I want to go over first, ask you guys an open-ended question. How did the homework go? We didn't have much time to do it in class, a little bit of time. Were there any major problems? Nobody wrote anything on Slack, so I assumed that everything was perfect, beautiful, easy. Yeah? Pretty straightforward? Okay. Yes, question?
I was just wondering if you could explain what the null command at the end of all the lines meant, because I read the little note about it, but I just don't totally get why it's there.
Sure. So I'll show you something. Let's see if I can do a quick live demo. No idea if this is going to work. Okay. Let's go like this. Whoa, what is happening? So I load a library, and then I'm going to, let's see, load chromosome. Let's see. Oh, data, chromosome. All right. So now I've got some data in there. If I go to my environment, this is here. If I click on it, I can see that there's some data. So let's go to ggplot. Actually, what I'll do to make it a little bit simpler is homework. I should have just opened the homework. Okay, so here, I also need to load tidyverse. Okay, so then here, if I come down and I run this, okay, I get a plot. Now, if I didn't have null at the end and I run this, I get a plot, all right? But now, let's say I want to comment out this line. It's going to take the scale off. This is what you guys probably discovered. And I run it, and nothing happens, okay? And the reason nothing happens is because ggplot is expecting something to come after this plus. So we'll have a ggplot lecture on Monday going into the details of it. But what ends up happening is we know about the pipe operator, which is and then. ggplot, for better or worse, uses a different operator to string different commands together. And they use the plus notation. So I'm going to make a plot, plus I'm going to add a point, plus some labels, plus minimal, plus ... Right? So it's not expecting anything. So this actually is just like a little trick that you can do, because then you can comment this out, just like I did. And what happens is null is nothing, right? But it at least is a defined nothing rather than an open-ended nothing. So sometimes I'll put this in my own code as I'm building it, just to make sure that I don't get these errors. So what ends up happening, if you go like this, what ends up happening is, oh no, let's take away null. Is that you can look down here, and you can see that this is still waiting for a command. So most of the time, this command right here, this little chevron arrow, is like when you're waiting to type something in. Here, it doesn't have it because it's like the program is saying, well, I'm still waiting for something. If I type in, if I come down here and I type in like null, then it finishes the command. It's expecting, okay, now I'm waiting for a new command, and then it plots it over here for you. Okay? So it's not something that you really need to know too much about. I do it sometimes in my own code, but it's just a way for me to have you guys go through and comment without breaking it on the last line. Okay. Yes, other questions?
For scale,
Mhm.
when you're setting the scale, what's the difference between labels and breaks? And how they relate to each other?
Sure. So if we go like this and we take off, actually we'll just run this and we'll look. So label, this labs command, this label is labeling the X and Y axis. So you can see that chromosome is here and base pairs is here. So when I get rid of this one, what happens is it will take the default labels of your column names. So this still says base pairs. It's just sort of lowercase, and this says ID. And we know what ID is, but that's not that informative. So we can override the default XY labels by putting them there. But there's other types of labels, including a title, subtitle, captions, and so on. Okay? So we'll go like this, and we'll give it a title and subtitle. One more thing. So breaks is, here, this scale Y continues. This is special, okay? So what this does is it's going to then not talk about the label of the X or Y axis. It's going to overwrite the units of the X and Y axis, okay? So this is totally accurate. It's just less intuitive, okay? So if I change this, I also change the label to indicate that it's millions, and then it's just a little bit easier to comprehend, okay? Because I know what 50 is, and then I know what 250 is, but I don't really understand like 25 times 10 to the 8th, okay? Clear? Okay, yeah.
So I think the problem with like if you graph different data on here, different data sets have different breakpoints, and so you need to like figure out what the breakpoints are, and then like because I was adding continuous labels to my graph, but it was saying that the labels weren't adding up, and I had to figure out, like I just had to go in and like test each number of labels until it finally worked.
Yeah, it's kind of a pain, huh?
I think though, if you just copy paste whatever you assign to your labels to your breaks, then you know that the labels and breaks will be equal. So as long as they have the same number, you won't have a problem.
Okay, so you just add the breaks equals and then
Exactly the same as the labels.
The list at the end of the Y continuous command.
Correct.
Yeah.
Okay. Other questions? All right. One of the things that we also talked about yesterday was installing packages. Okay. So we have a pop quiz, not announced. Don't worry. Okay. I would like you guys to install a package, and the package is called Cable Extra. You have to type it in exactly like this. This is not what you're going to type in, but I write it out for you to show you how to spell Cable Extra. So go ahead and do that in your RStudio Cloud environment. You will need that to view the help file vignette that Allie made. So if you remember how to install packages, install a package that has that KABLE So go ahead and do that now. Yes?
Is there any way that I can zoom in a little? It's really hard to tell.
Okay, let's see.
You can make your font bigger.
Yeah, the resolution is set here.
Yeah, but in R, you can make your font bigger. Go to Tools, Options, Global Options. And if you go down to like where you find your appearance and stuff,
It's the third
Oh, it's
one.
the
Yeah.
third one.
You can change your font size.
How's that? Better? We got more space. Yeah. Okay.
You can also change your background to black, which is easier to read.
Okay. So go ahead and talk to your neighbor. Ask your neighbor, did you figure it out? I figured it out. Did you figure it out? This is what I did. What did you do? Install a package. Yes?
I figured out my issue.
What was your issue?
I also have a Mac at home. I tried it on my Mac, it's different, like all sorts of different things, and it's Chrome. So I'm on Windows Edge and I'm
Great.
So
Good to
in
know.
case someone else has an issue with browser.
Okay. That's strange. Yeah.
She's on Chrome, I don't know.
Okay. Okay, and then,
Surface has a different.
so has everybody installed Cable Extra?
Pro too.
Yeah.
All right, now, one last, yes, question.
Object not found.
Object not found. That's because you're probably trying to install an object and not install a package. Is it in quotes? There we go.
Surfaces and Macs have different versions of Chrome, I believe, than base. Like,
All right, now one last thing before we get into the lecture for today. So, one of the things that I asked you to do was to go into the vignette directory and knit the students.rmd for you to then generate a data frame that has, hopefully, your name, a topic, a help file topic that you will tackle, and then a function, which will be the primary function that you'll be writing about. So, assuming that you did that, what I'd like you guys to do now is go to Slack, and in Slack you have a channel that says vignette, help file vignette. So go into that and just say, like one sentence that says, my vignette will be about the topic, and we'll use the function that you have. Now, what I want you to try to do, though, and this is going to get a little bit ahead of ourselves, but what I want you to do is I want you to write the function in backticks like this, okay? So within Slack, go to the Slack channel, it says help file vignette, and just write a quick sentence that says, my topic is this, and my function is this, and function, I want you to put it in backticks. Okay. So after you're done with that, we'll give you just another minute, and then Akshay will get going with the introduction to dplyr, class 2, all things data manipulation. So go ahead and just take one more minute to do that. Just make sure that this is there. So you can.
Awesome, thank you.
So the backtick is the key that is next to the number 1. It's not the quote. It's the backtick. On most keyboards. Yeah. Anybody's not next to the number 1? So if you want to delete, you can right-click and delete your message if you made a mistake. Or you can type it again.
Control L, right?
If I can move this down or hide it. Let's go. Yeah, let's just put this here. Oh, what did I do? Oh, that's what I wanted to do. Okay.
Yeah, so Control L. Go. All right. Akshay, the floor is yours.
All right, so today we'll be introducing you to the dplyr package. Just before we begin, go into the to_dplyr folder and open up the exercise RMD. Great. And as I proceed through the talk, you'll be going through this markdown file and executing the chunks of code. So data sets are very rarely in the exact form you need them to be in. And maybe you need to create a new variable, or you need to reorder your rows, or maybe you want to get rid of some rows. dplyr is a package that enables you to do this kind of data manipulation, which is also known as, sometimes known as, more frequently known as data wrangling. And before we, for this talk, we'll be using the proteins and subcell datasets within the Tidybiology package. So the first thing you should do is just execute the first chunk. So that's your setup to load the Tidyverse package. And then go ahead and execute the next chunk, which is
Actually, comment out
the install.
Yeah,
All right.
it should be on there.
Great. And finally, for this slide, load the proteins and subcell datasets, and you should see them appear in your global environments pane. Great. All right. Now, usually when you see a dataset that you're not familiar with, you want to have a sense of the structure of the dataset. So one useful function for allowing you to do that is the dim function. The dim stands for dimensions. And it gives you the number of dimensions of your data set. So in this case, if we want to inspect the proteins data set, we would just do dim and then put the proteins within brackets. And it gives you, in matrix notation, the number of rows, so in this case 20,430, and the number of columns, 8. That code executed? Cool. But dim just gives you 2 numbers, so it's useful but limited. To get a deeper sense of what kind of variables your dataset contains, you can use the glimpse function. And the syntax is the same, glimpse, and then you put in your data frame within the brackets. And here it's a little bit more explicit. Whereas previously you just had 2 numbers in your output, now you have, it explicitly says the number of observations. So observations are always rows, and the number of variables are always columns. So you will hear those terms used interchangeably a lot. And in addition to that information, you'll also see it gives you some information on the various variables or columns in your data set. So the first column is all the names. And then within those like pointy brackets is the type of variable. So CHR is a character variable. You'll see DBL, double, which we'll talk about in the next slide. And it also gives you a, it shows you what some of the entries are for each column. In Matt's talk, he introduced you to the dollar operator or function, and that's a base hour way of extracting a variable from a data set. So it's like a handy reminder. If I just wanted to see what's in mass, I would do proteins $mass. So the basic data types, and there are 6 basic data types. So there's a character data type, so it's generally anything you see in quotes, so like A or Tidyverse or my name. There's numeric, which can either just be like a nice round number or a number with a decimal point. And there's the integer that specifies, that's different from a numeric because it's only integers, so you won't have decimals. And the L in R after that number tells R that it's an integer. So you'll see this a lot in your global environment. So the L means integer. A logical is either true or false. It can only have one of 2 values. And then you have complex. So for the I is root -1 for imaginary numbers. And finally, there's a raw data type, which we won't cover, so I don't know what it is. You'll also see DBL a lot, double. DBL stands for double, and it's the same as numeric. For some arcane historic reason, there are 2 names in R that refer to the same thing. So don't be surprised if you see DBL, it means numeric. And factor, that's another really important thing you'll see. Factor, or FCT, is it's a collection of ordered character variables. So sometimes you will have like a set of names where order doesn't matter. It could be John, Jacob, Ali. Or you can have a collection of character variables where order does matter, like the month of the year. So if you don't specify the order, for example, in R, it will think the first month is April, just because it'll do it by default alphabetically. So there you would have to specify, no, it goes January, February, and so on. Right. Now, to find out what type of variable a specific variable is in your data set, you can extract it using the $, so proteins $length, and you can use the class function. So in this case, it should be a numeric, and it is a numeric. Also, could you just double click on the proteins data set and just quickly inspect it? You'll see it has uniprot ID, gene name, length, mass, just to get a sense of it. Cool. In maths, Matt introduced you to the pipe operator, which is percentage sign greater than percentage sign. So the pipe operator is a way of chaining together lines of code in a way that makes it both easy to understand and easy to read. For example, you have this chunk here. So what you're doing is you're taking your proteins data frame. That's always the first argument that goes into your select function. So when you see pipe, think and then. So you take your proteins data frame and then you pipe it into your select function. And what select does is it selects specified variables. So in this case, you're just selecting uniprot ID and length, and you're discarding everything else. You then just take those two variables and you pipe them into the filter function. And the filter function works on rows. So the third line will only select rows or filter rows that have a protein length greater than 500 amino acids. So if you execute that code chunk, you'll see underneath the code chunk the output. Just one quick thing. For the purpose of the talk, I've piped everything into a head function. What a head function does is it takes an input and returns only a specified number of rows. So in this case, 1. And the reason I did this is just for the sake of brevity. But you won't see a head function there. You'll see the entire output. So in my case, I have an output that only has 1 row because of the head function and 2 columns. But you should see 2 columns and 20,000 rows. And the chunk that you get, actually, let me go to it. Our markdown handily, it nicely only will show you your data 10 rows at a time. So these are the first 10 rows, and then if you wanted to see the next 10, you can go down here, and so on. Also, just kind of a side note, you'll see this Tibble. Tibble is a tidyverse. It's a special kind of data frame. It's effectively equal or equivalent to a data frame. It's just that when you run, if you take like your proteins and you just wanted to, if it were a data frame and you inspected it in your console, R would just output 20,000 rows, which isn't useful. But if you converted it to Tibble, it would only show you the number of rows that fits in your console. So it's like it's made to fit in your console. So it's just an aesthetic difference. So just to reiterate, this code chunk takes proteins, pipes it into select. Select chooses the specified columns, and then pipes that into the filter command, which then filters rows that correspond to proteins that have a length of greater than 500 amino acids. So when you see that pipe operator, always think and then. Also, it's kind of annoying to have to go percentage sign greater than percentage sign, but if you go in on a MacBook, if you go Command Shift M, and on a Windows machine, if you go Control Shift M, that's a shortcut to getting a pipe. The alternative to using a pipe operator is to just have one long line, which I suppose you could argue is more efficient because it's one line as opposed to 3. And if you execute that chunk, you'll see that you get the same output. But this is a lot more error prone because it's super easy to miss commas and brackets.
As a heads up, on a Windows machine, if you Control Shift N, you'll just get a new document. So
I do that all the time. All right, so the dplyr package consists of various functions of verbs, and we've already been introduced to 2 of them. Well, more than 2, a few of them. So some of the things you can do, in the dplyr packages, as I mentioned, you can select rows and columns based on certain conditions. You can create new columns or new variables. And you can also obtain summary statistics like mean or median of numeric variables. And so these are the functions we'll be covering today: select, filter, arrange, mutate, and summarize. And finally, there's a group by function that works with these functions. So the first function is select. So select only applies to columns or variables. So the most basic select function is where you take a list of column names that are comma separated as input. So for example, from the proteins data frame, if you just wanted, as previously, if you just wanted the uniprot ID and length columns, you would do this. And if you run that chunk, you'll get something similar to mine, except again, in my case, I only have the first row, you'll have 20,000 rows. Cool. If you wanted to select everything except uniprot ID because you want interest in that for whatever reason, you can run this where you do minus whatever your variable name is, and it'll exclude that and only output everything else. I should say when you run code chunks like this, the output you get is temporary. It's not saved. So to save and output in R, you always have to assign it to an object, which we'll do later on. And this is fine for now, but presumably when you're doing your own analysis, you'll want to save some output. So this is what it looks like. Right. Let's say you, in this case, I think there are only 8 variables. Let's say you had 800, and you wanted to select 300 variables. Now you could type them out manually, which is inefficient, or if they're all in a row, what you can do is you can use colon, and what that does is it takes the variable on the left hand side of the colon and the variable on the right hand side, selects those two and everything in between. So if you run that code chunk, you'll see that this selects 4 columns: the uniprot ID and protein name, and the 2 that are in between, gene name and gene name alternative. Cool. Right, so that is select. And if you could do a quick exercise, so that code chunk will be empty. And if you select the following columns from the proteins data frame: uniprot ID, sequence length, and mass. Give you like a couple of minutes.
Overly complicated. There's 2 different ways to do this. You can select your data frame and then, so you select or start with your data frame and then select the things that you want from it. The other is if you go to the help tab, or you go to the select help from your console, you'll see that select can run by itself. You can start with the object that you want to select. You don't need to pipe anything to it. So when you see something like this, you say select, the first argument is your data, in this case a data frame, and then from here the other arguments are the expressions of the things that you want to select. So if I were doing one line of code only, I would maybe write something like this: select, my data frame is proteins. So hit enter a bunch of times to make it, scroll just a little bit so we can see it.
Scroll.
So like this. Okay, so it's 2 fingers to scroll. So you can see select, that's the object I'm selecting from, and then my arguments of the things I want to select. But if I was more likely, I would put this into a pipe and chain these together, where it's proteins and then select. And you don't need to write proteins again, because it already knows. It's receiving the information of proteins from the pipe from the previous one.
So in this example, you could say, all right, this is actually easier to do than a pipe, and you'd be right. But it's good to get into the habit of writing pipes or using pipes. All right, so this is a solution. You could just like type them all out, or you you'll see that sequence, length, and mass are all in a row. So you can just do comma, sequence, colon, mass. That's a solution. So the filter verb, moving on to the filter verb, this function allows you to select rows based on a certain condition or conditions, and it discards everything else. So all filters are performed on some kind of logical statement. So any kind of statement that produces a true-false output. So if a specific row meets the condition you set, or i.e. is true, it gets selected. If not, it gets discarded. So you can perform a filtering operation on categorical data. So in this case, it's like groups. So for example, this is using the subcell data frame, which has information on subcellular location of proteins. So let's say I was only interested in proteins that are associated with the ribosome. So again, you take subcell and then you pipe that data frame into the filter function, and location is the name of a variable. And you do the equality operator, so equal, and then I only want ribosomes. So I do ribosome, and you make sure that you put it in quotes. A common mistake here is to go location equals ribosome. If you do that, you're trying to assign ribosome to location, which is, you don't want to do that. You will get an error. So if you're doing some kind of like logical operation, so in this case equal to, you have to do equal. And again, I've typed that into head, so you'll only see I will only see the front row, the first row. You will see everything. So if you inspect the output, if you look at the location column and you scroll down through it, you'll only see ribosome. So it confirms that you've only selected rows that have ribosome in the location column. Great.
Is location just like a general word?
So location in this specific data frame refers to cell locations within the cell.
Okay. How is that defined?
For this data frame, it's like ribosome, mitochondria, and cytosol.
Okay.
But it's specific to that's a good point. This is only specific to this data frame. Like if you piped in proteins into this code, you'd get an error because there's no location variable in proteins.
If you click on the data as well, you can like scroll down and see what information systems.
Right, and you can also use numerical data for a filtering operation. So, for example, let's say I wanted to select proteins. So this score is I guess it's like a confidence score. Like how confident are you that certain proteins associated with a certain location, with 5 being very confident. So let's say I'm only interested in location scores greater than 4. So I only want like high confidence scores. I would run the following code. So again, this is identical to the previous line, except the what goes into the filter brackets. So in this case, it's your score greater than 4. And if you run that code chunk and inspect the score column, you'll only see numbers that are greater than 4. And also, this data frame, this output has fewer rows because you're filtering out stuff that's less than or equal to 4. Oftentimes you'll want to filter on multiple conditions. So one way to do that is to just string together multiple filter commands separated by the pipe operator. So let's say I wanted to select proteins that are associated with the ribosome and have a location score greater than 4. So doing the previous 2 things together. You could do it like this. You pipe in your subcell into the first filter command that only selects proteins associated with the ribosome. You take that output and you filter that into the second filter command, which only selects proteins with a location score greater than 4. And this is the output. A more efficient way of doing the previous thing is, because for example, these were only 2 conditions, so it's it's fine to do 2 filters. But let's say you had 50 conditions, and so you have like, instead of having 50 rows of filter, 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 you can just have one filter command and put in all your conditions within that filter and separated by commas. So this code chunk does the same thing as the previous one, except you just have one filter command. And you have 2 conditions and they're separated by a comma. The comma, you can read that as AND. So you want proteins that are ribosome located and have a location score greater than 4. And if you run that code chunk and you compare it to the output of the previous code chunk, you'll see it's the same. I think that's it for filter. So again, quick exercise using the filter command. So I should have specified. So you would, in this case, use, again, the subcell data set, not the proteins. So using the subcell data frame, filter all proteins not associated with the ribosome and with the score less than or equal to 4. So just as a hint, just as equal was equal to, exclamation mark equal or bang equal means not equal to, and less than or equal to operators less than or equal to.
It will feel awkward at first, but get used to the keyboard shortcuts for the pipe operator.
Definitely.
It's worthwhile.
Mm-hmm.
Yeah, I couldn't tell you what it is, but I could do it myself.
Yeah.
Like I couldn't verbally tell you what it is.
I had to remind myself yesterday. So also as a hint, if you just copy paste the previous code chunk and just change a couple of things, you'll get the right answer.
So a couple of things just to remember. There's something that's called a style guide, which is sort of the style of how you write your code. Now those will become a sort of intensely personal a thing. But there's a couple of conventions that will be important here. So when you say filter, you put the parentheses right after filter, because if you don't, filter looks like an object, right? It's a non-quoted word. But if you put a parentheses after it, it knows that this is now a function, and then it does everything within the function until it sees the back end of that parentheses. So that's important. When you see the spaces around the pipe operator, you can have space or you don't. I like to put space. Allie doesn't. I like to let my code breathe. I like to let my code breathe a little bit. I corrected a bunch of Allies the other day, preparing for the lectures. So there are some things that matter. There's some things that don't matter. Like here, again, head, that's a function, right? So head needs to come right after the parentheses. So just, again, there's going to be some things that are style, and there will be some things that are absolutely crucial. Otherwise, R will get confused. Again, this is like the language, to learn how to speak the language.
Oh, I don't put space before my buses. Is that what you're talking about?
Oh, yeah.
I put it before pipes, not before buses.
Let your code breathe a little bit.
Also, these like little spaces before filter automatically does that to you, but it doesn't strictly have to be there. Everything can hug the left margin, but it's nice. I don't know. I've gotten used to seeing it like this, and other people's code also looks like this, so it's just nicer to see. But it won't break. Actually, you could put this all on one row if you wanted to, but then it would go beyond the right-hand margin, so that would be maybe problematic. Should I go ahead and...
Anybody have any problems with that exercise? We don't have it done yet?
Cool. So yours should look something like this. I'll show it again. Okay, a range. So a range is a really simple function. It allows you to rearrange your rows, arrange your rows. So if you arrange based on a numeric variable, it'll by default arrange from the smallest to the largest or the shortest to the longest. So for example, if you wanted to go from your shortest to your longest protein using the protein's data frame, you would run this code. So you take your protein's data frame, you pipe it into the arrange verb, and since you want to go from shortest to longest, you would use your length variable. If you execute that, you'll see you go from something that's 2 amino acids long to something that's much longer. And in this case, I put a head 3 just so that you could see the top 3, but you don't see the length variable here, so it's not very useful. But in yours, you'll see it'll be an ascending length. Now, let's say you wanted to go the other way around, from longest to shortest. It's almost the same, except you would put a descend function within your arrange. So again, this looks almost identical to the previous one, except you put descend within a range, and the argument that goes into descend is, again, length. And it looks like this. And Titan's the longest one. Yeah. Alright, so that's basically kind of all you can do with a range. So the quick exercise with the range is what happens when you apply a range to a categorical variable. So choose either data frame, proteins, or subcell, and pick whatever non-numeric categorical variable you like. Apply the arrange function to that, and look at your output. Like, what is R decided to do with a categorical variable? So what I did was, as a solution to this exercise, is I took the proteins dataset and data frame, and I picked the gene name alt character variable, categorical variable, and when you run that, so this is maybe not the best example because within this character variable there are numbers also, and numbers aren't letters, but in R it goes, the order is 0, 1, 2, 3 to 9, and then A, B, C, D, E. So categorical variable will arrange it in alphabetical order. All right, so all the functions introduced so far, they don't create new variables. So mutate is the first function that generates a whole new, one or more new variables. So if you run the mutate chunk, what this does is, again, you take your proteins dataset and you pipe it into the mutate function. It takes the length variable from the proteins dataset and applies a square root function. That's what the sqrt is. And it takes the output of all those 20,000 something square roots and assigns those values to a new column called square root underscore length. So if you look at your output, you'll see that instead of 8 columns, there's now 9. And by default, whenever you create a new variable using mutate, the new variable or variables will appear at the end. So your last variable here is called square root length, and it's the square root, contains the square roots of the lengths of all the proteins. So in the previous example, we just used one variable, length, to create a new variable, square root length. You can combine different variables within your data set to create a new one. So, for example, if you wanted to normalize protein length to protein mass, you could run this. So in this case, again, you are taking your proteins data set, piping it into the mutate function. You take your length and mass variables, divide one by the other, and you assign the output of that to a new variable called protein length underscore mass. And again, if you look at your output, that's the last column. Right.
Question?
This doesn't update the protein data.
Good point. It doesn't. So the output you get is temporary. Your original proteins dataset is unchanged, and actually that's a good convention. You might be tempted. I frequently do this, which is not good practice, is to overwrite your original dataset. You could assign this output to proteins, and it will overwrite the previous one. But if you wanted to make a new data frame, it's best to create a new object called proteins new, something like that. And so it generates a new data frame. But yeah, the original proteins remains unchanged. I went through that kind of quickly.
I mean, that's really important. So I'll just pause and interrupt. Do you guys understand that point? Yes? No? Really clear?
Like for the sake of this example, like I could run the arrange thing. Oops. Right, and it looks like this, but this output isn't saved anywhere. If I did the assign operator, which maybe I should have introduced this before, but I'll introduce this in a couple of slides, and call this proteins new, and I run this. If you look at your global environments, now there's a new data frame. It's called proteins new. And if I click that, there's a new one. And it's kind of hard to tell here because I've just applied a range, so I haven't created any new, I haven't filtered anything out or changed the columns. But here it'll be a range. The order of the rows will be different.
Yeah, you can see row 1 is type.
Oh, there we go. Okay, yeah. And I don't want to do it here because I'll continue to use proteins. If I did this, the original proteins data frame would be overwritten. Right.
Yes, question?
For the sake of this class, is it being overwritten to Tidybiology?
No.
Okay.
No. Any changes that you make is just in your environment. So that's why you guys all made a save a copy, and that's why we're using the RStudio Cloud. So that's yours to break. But if you needed to, let's say you overwrote something that you didn't need to, what you would do is you would just close that R Markdown or something, and you could open up, you could actually load, you wouldn't even need to close it, you could reload the original data that's in the Tidybiology package. So you're not actually overwriting anything in the package. So like the package has data in it, and that first command that says data proteins, that's then essentially extracting data from the package and putting it in your environment for you to do something with. So if you did make a mistake or you needed to start fresh, you would just say, you would overwrite the proteins data frame in your environment by just running data proteins, and that then overwrites it. Just like if you assign an operator, or you assign anything to proteins, it would also overwrite it. That's a good question.
What time does the class end? 11:40? Oh, weird. Oh, right, I should say something. So the mutate exercise, so for this exercise, if you could use the proteins dataset to make a new variable, call it whatever you like, that contains the values of the protein lengths divided by 100. Just to remind you, this is the syntax of the mutate function. Mutate new variable equals existing variable, and you've done something to it. All right, so this is one solution. So this code takes your proteins data set, pipes it into the mutate function. You take your length variable, divide it by 100, assign it to, I called it protein underscore length underscore 100, and you get a new column. All right. The summarize verb it does what it says. It takes one or more variables and it gives you a summary statistic of those one or more variables. So for example, if you wanted to calculate the mean of the length and mass columns of the proteins data set, you would run this code. So you take proteins data set, you pipe it into the summarize function, and then you do mean length variable, comma, mean mass variable. And the output of this, unlike all the previous outputs, is a very small one. It just has one row, and that's the mean length and mean mass. So this is a really intuitive, simple function within the dplyr package. Now, let's say you wanted, so in this previous example, R just calls the new columns mean, length, mean, mass. Let's say you wanted to give your own names to it. You would run this chunk of code, which is very similar to the previous one, except you take your mean length and you assign it to a new variable. You give it a name, and you take your mean mass and you do the same. You assign it to a new variable. So the only difference between this output and the previous one is this has nicer names. But this is a really minor thing. You could just do summarize, mean, your variable, and you'd get the same output. Oops, yeah. So that's really all you can do with summarize. So for the summarize exercise, you make a new table where you calculate or you report the mean, median, and standard deviations of protein lengths. Again, using the proteins data set. So to get the mean, you would use the mean function. To get the median, you would use the median function, which is just median, open close brackets. And for standard deviation, the function is SD, open close brackets. And again, I'll go back just to, this is what your syntax should look like.
You can also write this function with a Z, just in case.
Oh yeah, Tidyverse is tolerant of different alternative spellings. So like it accepts, so in ggplot you'll see like for the color argument, you can either go COLOR or COLOUR, and it still works. All right. So this is one solution. So this way you get like pretty names. You assign names, but you can do it just as well without these protein underscore mean equal. You can just do mean length, median length, SD length. And your output again should be just this. You get 3 columns, 1 row. Cool. All right. The final function we'll be introducing today is the group by function, and group by works nicely with the other functions introduced. So in this talk, we'll just discuss how group by and summarize work together. So previously, you saw like summarize mean length of all the proteins, but let's say you're interested in if we had a subcellular location in the proteins data set, you were interested in mean lengths per region, you would use group by. So you basically do the same thing, you do the summarize, but by different groups. This should hopefully make it clearer. So for example, if you wanted to know the mean location score of proteins in each location, you would use group by. Because if you just did subcell, pipe that into summarize, location, you'd get 1 number. That's just the overall location score, overall mean. But if you did subcell, you execute this code, you group by location, and then do summarize mean score, this is the output you get. So the 15 rows correspond to 15 different locations in this data set, so ribosome, mitochondria, and so on. And then you get 2 columns, one for the location, and one that has a mean score within that location. If you didn't do this group by, your output would just be 1 row, and that would be the mean location score for all the proteins. Right, so there's no exercise for that, that's just group by. So let's say you wanted to, so far everything we've done, we've just made a temporary output, but you want to create new data frames based on the analysis you've done or the wrangling you've done. For that, you have to assign your code chunk to a new object. And you can either do the left-hand operator or the right-hand, and it works the same. But for the sake of doing the if you were following the style guide, you would do the left-hand operator, although I constantly use the right-hand one. So for example, the previous code chunk, if you wanted to save that, you could do something like this. You have your code as is, and then you use the left-hand operator to assign it to a new object, which in this case I've called subcell_new. So if you execute that chunk and you look at your global environments, you'll see that there's a new data set called subcell_new. You double click on that, you can then see the output or what it contains. If you wanted to save that, so this is right now a data frame within R, but it's not saved on your computer. If you wanted to save it as, for example, a CSV file, you could use this handy write_CSV function, which is within the tidyverse. And this takes in just 2 inputs. It takes your new data frame, so you have to create a new data frame. And that's the first argument, comma, and then the name of your CSV file. So your name could be whatever you want, .csv. So if you execute that chunk and you look in your files, you'll see a new file has been created, and it'll be called subcell_new. And so you have a CSV file now. Cool. Now, if you want to know more about the dplyr package, all the packages within the tidyverse and kind of packages in general come with vignettes, which are really handy guides for using that package. So dplyr has a set of vignettes, and to access those vignettes, you can run this function, browse vignettes with a capital V, and dplyr in quotes. If you run that, you might get a pop-up blocker, but if you ignore that, you will get it'll take you to a website, and it'll have a list of all the vignettes that are within this package as in HTML and also in just R code, which these are all really useful, these vignettes.
So another way to get to it, I'll do that again slowly. So come to your help pane, which is over here, and just type in dplyr, dplyr. And what you'll get is the info page about the package dplyr, description, details, and so on. Maintainer, authors, contributors. If you go down here and click on index, all the way at the bottom, you'll get all of the help pages and documentation for the entire package. You can see it's quite rich. But the second one here is going to be user guides, package vignettes, and other documentation. If you click on that, it will lead you to the same sort of page, same options as typing it in. And then what you can do is click on any of these vignettes. You can click back, and it will give you the information for the dplyr vignette, the introduction vignette.
Thanks, Matt.
And this would be another useful opportunity to then highlight one of the two sort of final projects will be your creating a vignette. So rather than creating just like a help page, what we want to do is have you, with your fresh eyes on a problem, how do you solve a problem? Well, we gave you the function that will likely be the most useful to solve that problem. But so you can spend some time with the vignettes, and essentially what we hope for you to be able to do is to, over the next 2 weeks, is to be able to create a vignette about solving a problem using a single function. All right, so Ali and Akshay have provided some examples. That's in the help file vignette directory within the RStudio Cloud. So you can spend some time with vignettes, but really think of them as rather than the help file, which is a function-centric documentation, the vignette is a problem-centric documentation that helps you solve a problem. And in some cases, you can even have a vignette that's an introduction to an entire package. But most vignettes you will see solve a problem, and then they will walk you through that problem with a combination of plain text and code.
Cool, and that's it for the talk. In preparation for this, I watched the talk by Hadley Wickham. So he's the guy who has led the development of the Tidyverse. And he introduced his talk by saying, with these functions, you should be able to do like 90% of all the things you need to do. So they're just a few functions, and compared to Basa, which has like thousands of functions that can do these things, this is, it's a much shorter list of functions. And you have things called helper functions that you can put within your filter and select things like ends with. So you just filter things that end with RNA, things like that, and it can get more and more elaborate. But just with this, you can do so much. And as an exercise, if you would like, you just click on the homework RMD, and this essentially goes through the same things we went through in the talk, but using the chromosome dataset. And there are some questions I've put in that should help reinforce these concepts. If there's any issues, just post it on Slack.
So you have a little time now. So
Yeah.
you can go ahead and start on this now if you'd like. Or if you're hungry for lunch, you can run to Nosh or something. So we'll hang out. We'll spend a little time now, help you guys through some of these problems. And then just one last thing to mention to you. So part of the reason that we have these both exercises and homework files is to give you guys the code, right? Because I said to you that we are envisioning the impossible for you, is to go from nearly no knowledge of R in 5 classes to doing an entire analysis de novo of a data set or data sets that you really know little about to extract some interesting biological insight. That's a tall order, right? I have faith in you guys, don't worry. But one of the things that we want to do to help is to provide you with examples that you can then use, both the code, but also the ideas that you can then use for your own project, right? Because the main sort of summary and the main wrap-up for this entire course will be your short presentation of what you did, how you did it, what you found, and what you would do to test it. So if you go through these examples, what you should be able to do is then begin to learn about these data sets and be able to use some of the code then to apply it to your final project. Okay? Thank you, Akshay. Thank you. So it's, again, 11:35, so you've got a little bit of time. We will have class 3 on Monday. This is going to be a dive into visualization. So Ali will be giving a lecture on ggplot, which is a package that is all things data visualization. So as Akshay said, if you have questions over the weekend as things come up, then reach out on Slack. We're here to help. All right, that wraps up Tidybiology for today. Thank you for watching. And if you have any comments, go ahead, put them below. If you like us, give us a thumbs up. If you want to see more of this, go ahead, hit the subscribe, and you'll see all of the videos that we post about Tidybiology. Thanks, see you again.